So CapeSym recently added ability to do a thermal analysis on flip chips and extract an RC equivalent network that we could bring back into the electrical simulator and do coupled electrothermal simulations. So we wanted to demonstrate this for a gas power amplifier design, and we solicited Mike to help us with this, and he initially agreed to do it. And the last minute he decided to attempt a silicon germanium HBT design, even though he didn't have much experience working with that particular type of device. So he solicited some help from Brian, Graham, and Renee, but he didn't get very far. He wasn't able to provide a design to be flipped. So basically I'm going to give you the slides that he gave me, which takes the design as far as he did. So CMYC is a thermal analysis tool that's integrated with Microwave Office that gives RF designers the ability to do a more temperature-aware design. Like I mentioned, you can not only get a thermal analysis to detect just how hot your devices are getting, but you can also bring that temperature information back into your electrical simulation to actually see how it's going to affect your performance. So Mike set out to build a Bluetooth power amplifier that would provide 100 milliwatts at the antenna for a small die area. His idea was to follow a typical gallium arsenide MMIC design flow. And so, you would start with the IV curve to size the transistors, then you would do your linear design and then refine that with more sophisticated analysis that included EM effects and thermal effects to sort of refine your design. So for this case, if you assume a 30% power added efficiency, you would need about 400 milliamps, which implies for this particular technology that you would need about 600 individual silicon germanium HBT cells to get that. So what are the potential issues? Well, as a gallium arsenide designer, the things you might be worried about for thermal might be something like thermal runaway. So in a typical gallium arsenide HBT, you have to worry about each cell sort of running away with the current if it gets too hot. So if you have multi-finger HBT and you have the center finger is getting hotter, then you can have current collapse where that center finger winds up taking all the current and the current on the other fingers goes to zero. But in the case of SiGe, what you have is you have a bunch of very small cells that you put together to get your total current. And so with those, you have to worry about, now I have a lot of little heat sources in a small area. If I put them too close together, my peak temperature could be too much for the silicon process that it can support. And then, of course, the other issues that you have different from gallium arsenide design are just different materials, and you don't have any backside metal on the silicon, no through Fias that might help you with thermal. So apparently Mike was frightened by this paper from 12 years ago where they looked at silicon germanium power amplifier design for a CDMA application, and they made a big deal out of this positive thermal coefficient where you have to worry about this thermal runaway issue. And the way you deal that normally with a gas HBT is you add some kind of ballasting resistors on the base or the emitter to help prevent that from happening. But in reality, it looks a little different. Mike found out when he started using the silicon germanium process from IHP's foundry. So there's a PDK for this, process design kit this for Microwave Office, so it was relatively easy to start doing design with this. And we created a template for these device arrays that would serve as the thermal process design kit for this particular process. So in the HBT model, in the transistor model, in the design kit that's provided by the foundry, you have self-heating effects already included in that, and those have been validated with measurements by the foundry. But the big problem we found when we did our initial thermal analysis is that if you just take 600 cells, and you put them in a big array, say 20 by 30, that's a pretty small area to dissipate over a watt of power in silicon. And so you wound up getting a peak temperature of around 180 C, which exceeds the maximum temperature for this process. So it's pretty clear that you have to do something, rather than just making one big array. And the other interesting thing about the thermal effects in this, is that you see both positive and negative feedback. So in this graph here, for example, we're showing on a 20 by 30 array that if you do a temperature sweep in microwave office, what you find is that at low temperatures you have a positive effect. So as it heats up, it produces more current. But then as it gets hot enough, then you start having a negative effect, where as it gets hotter, it reduces the current. The other thing to know is that as you change the shape of the array, you actually can change the shape of the IV curve because of these thermal effects. So this shows two IV curves, one for a single array, 20 by 30, and the other for 6 100 cell array, or 6 device arrays, each having 100 cells. And so you see you get a little bit better DC bias with the 6 arrays. So the way CapeSym works is you can take a layout from microwave office, export it, do a thermal analysis, and get your temperatures and bring them back into microwave office. And you can evaluate sort of how the different layout of your arrays would affect thermal performance. You could also easily include solder bumps in that type of analysis. So they would just be other things that you would lay out, and you can optimize the layout of the solder bumps relative to your devices to improve thermal analysis. So you wind up being able to very easily evaluate different layouts for the best thermal performance. This shows, for example, a series of simulations done with CapeSym, where you change the spacing between the arrays, and so as you move them farther apart, up to a couple hundred microns, you start to see improved performance. So this is for 3 different levels of total power, and it's just showing the peak temperature over all the whole chip. So the other interesting thing is when you go to the 6 device arrays, smaller device arrays, you actually shift where that switch from positive effects, thermal effects, to negative thermal effects occurs, and you can actually shift it way down beyond your desired operating range. So these 2 things motivate you to basically use your thermal analysis to optimize the size of your device arrays and their layout, and then you can start your design. So then you can do your linear design. In this case, you need to do, unlike gas, you have to do off-chip impedance matching and inductors. And then this shows the nonlinear design, so the actual performance in terms of power added efficiency, output power, and gain. And you can meet your performance or the goals he set out for. He met with this design. So the interesting thing here that he gained from trying this was that basically you couldn't just save thermal till the end. You really need to consider up front how it's going to affect your very initial design in terms of how big of arrays you're going to make and how you're going to lay them out. And that's probably a little different than a gallium arsenide PA design, where you might leave thermal for the very end if you did it at all. And that's all I have. If I have any questions I can take.